Hello everybody. How are you? Ready for some fun? Perfect. So welcome to my session about In Memory OLTP, which is a completely new feature in SQL Server 2014. Who has already heard about In Memory OLTP? Who has already worked with it? What do you think about it? Good, bad?
I haven't tried it yet, but I'm looking to try and improve the performance of some of our updates and transactional-based updates, where we're maybe impacting tens of thousands of records in a small space of time. So that's what I'm doing.
Cool. Okay. So in this session, I want to give you an introduction to In Memory OLTP, why Microsoft introduced that technology in SQL Server 2014. We will see how we can work with In Memory OLTP, and because it's just a version 1 implementation, we also have to look on all the various limitations that we currently have with that amazingly new technology. A few words about my person. My name is Klaus Aschenbrenner. I provide with my company SQL Passion across Europe, SQL Server trainings and consulting services. I'm also a Microsoft Certified Master for SQL Server 2008, which was the highest technical certification that you could have achieved on SQL Server. I say was because that certification was just retired by Microsoft because they haven't made any profit out of it. So really strange story. I've also written the book Pro SQL Server 2008 Service Broker, which was published with April in the summer of 2008, so already a very long time ago. Service Broker is an asynchronous messaging framework that Microsoft first introduced back with SQL Server 2005, and with Service Broker you're able to write asynchronous message-based applications. Who of you is working with Service Broker? Just a few of you, so as you can see, I'm mainly working with things that nobody cares about. No, just kidding. You can also follow me on Twitter, and you find further information about my services about SQL Server on my webpage on sqlpassion.at, where you also find a lot of free training content around SQL Server. Let's have a look on the agenda for the next 90 minutes. The first step, I want to talk about the challenges why almost every database vendor provides us in-memory technologies. SQL Server provides us in-memory technologies, Oracle provides us in-memory technologies. The same happens, for example, for SAP. In the first step, I want to give you an overview why we now need in-memory technologies and what are the challenges behind it. The next step, we will look on the implementation of in-memory OLTP in SQL Server. So I want to show you what in-memory OLTP is and how you can work, and also how you can migrate your existing databases to that new technology. And in the end, I also want to talk about limitations. As I've already said, in-memory OLTP is just a version 1, means we have a huge amount of restrictions, and therefore currently you really have to decide if you really want to use that technology, because you are paying a lot for it based on the restrictions that you have in your database when you use that new technology. Let's talk in the first step about the challenges that we are currently facing. When we look on our storage subsystems are currently very slow. Who of you has a very fast performing storage subsystem? Almost, really? Wow, you lucky guy. But as you can see, almost nobody says today that we have very fast performing storage subsystems. Normally, when we deal with storage subsystems, we have slow rotational disk drives, means when we access those drives, A physical disk head moves forward, backwards, the platters are just rotating, means when we are reading to that storage, when we are writing to that storage, we have latency times of milliseconds. So very, very, very slow. On the other hand, we also have already SSD storage, SSD disks, very, very fast. We have latency times of nanoseconds and very, very expensive. Let's think about main memory. Main memory, very, very fast. We have also latency times of nanoseconds, and main memory compared to SSD storage is cheap, very, very cheap. When you nowadays want to buy 32 gigabytes of RAM for a database server, it costs you just a few €100, a few £100, so not really too much compared to our expensive SSD storage. So that's the first problem. We can't store our data in a very, very cheap and very, very fast way. On the other hand, when we look on our CPU clock speeds, the CPU clock speed is not really scaling anymore. Who of you has a CPU with 10 gigahertz? Nobody. As you have seen over the last years, clock speeds were going up and up and up, and now we are somewhere at the plateau at around 2 to 3 gigahertz. More is not possible because of the introduced heating. What are doing the CPU vendors? They are providing us a lot of different cores within the physical CPU socket. So when you currently look on Intel processors, AMD processors, it's not really a big problem to buy one physical CPU socket which has, let's say, 20 individual cores. Of course, when we look on the software which runs on that CPU socket, it's very, very important that the software can use all those cores concurrently. The problem that we have with relational databases is the fact that the relational database doesn't really scale linearly. Means, let's say you have 100 users on your system, 100 users are giving you a throughput of, let's say, 1000 transactions per second. When you increase the user load to 200 users, you will not have 2000 transactions per second, because a database doesn't really scale very well because of the introduced locking and blocking. Means every time when we read records, when we write records, SQL Server has to lock those records. Means users are just blocking each other, users are just waiting on each other. Means our throughput doesn't increase linearly. And internally, when SQL Server accesses shared data structures, like data that we have put in main memory, SQL Server internally use a concept called latching. Means when you read a memory region within SQL Server has to lock that memory region in main memory so that nobody else at the same time can write that memory region. Means with latching, you have blocking directly in main memory. Means as a conclusion, our relational database doesn't really scale very well. So those are the current challenges that we are dealing with when we are talking about relational databases. I have here a nice picture, and on that picture you see, for example, that blue line, and the blue line is just the CPU clock speed. And as you can see, over the last years, the CPU clock speeds are not increasing anymore. As I've already said previously, we are stuck at around 2 to 3 gigahertz of clock speed. More is currently not possible. Means we have a finite set of CPU cycles, and we have to use those CPU cycles as efficient as possible. As we will see later, In the case of SQL Server, when we run queries, SQL Server doesn't use those CPU cycles very efficient, because every execution plan in SQL Server is always interpreted, and interpretation means a huge amount of overhead regarding CPU cycles. Means when we now look on all those various programs, we mainly want to have a technology which stores all our data in main memory. Means we don't want to access our physical storage anymore. Of course, at some point in time, we still have to write our data to physical storage, because otherwise we would lose our data when our database crashes or when we're restarting our database. That's the first thing that we want to have. In the next step, we want to execute queries in our database with the least amount of clock cycles. As I've already said, we only have a CPU clock speed of 2 to 3 gigahertz. More is not possible, means thank you. Means we want to execute our queries with the least amount of clock cycles. With a finite set of clock cycles, 2 to 3 gigahertz, and we want to make as much work as possible in that set of clock cycles. And in addition, we want to have a technology that avoids completely the whole locking, blocking, deadlocking, and latching inside our database. Means when there is no locking, there's no blocking, when we have no latching in main memory, our workload can just scale linearly. And guess what? That technology is In Memory OLTP in SQL Server 2014. In Memory OLTP itself is based on 3 different pillars. So-called In Memory Optimized tables means when we create a table in SQL Server, we can tell SQL Server that we want to hold that table entirely in memory. Means when you're reading from that table, you're always reading only from main memory. You're not reading from your storage subsystem. When you write to your table, you also write only to main memory, and SQL Server just asynchronously writes out to your storage subsystem if you want to persist your data. You can even tell SQL Server, I don't care about my data anymore. Means in that case, when you're restarting SQL Server, you also have lost your data in your table. Not really recommended in every possible scenario, but for example, think about staging tables in an ETL process when you are populating your data warehouse. When that process crashes, you don't care about that because you just restart that process. Just think about it. Temporary tables, session state tables, they can be good candidates for memory optimized tables which you don't want to physically persist in your storage. In addition, we have a so-called native compilation. Means when you create a stored procedure, by default in SQL Server, the execution plan of such a stored procedure is always interpreted during runtime. And the interpretation just means we need a huge amount of additional CPU instructions, means the current amount of CPU cycles is not really used very efficiently in SQL Server. With native compilation, you can tell SQL Server that you want to natively compile that stored procedure to machine code. Means when you afterwards run that stored procedure, you are just running native assembly instructions. The stored procedure itself is not interpreted anymore. Means you can make a larger amount of work in the finite set of CPU cycles that you have available for your CPU cores. In addition, In Memory OLTP is based on completely new indexes. So when you work with In Memory OLTP, there are no clustered indexes. There are no non-clustered indexes. In Memory OLTP has no idea about those traditional indexes because within Memory OLTP, SQL Server uses indexes which are lock and latch free. Means we have a so-called hash index which is based on a hash table internally, and a so-called range index which is based on a variation of the B tree which SQL Server normally uses for clustered and non-clustered indexes. And both new indexes, the hash index and the range index, are just data structures internally which allow optimistic concurrency without locking, blocking, and latching. Means when we use those indexes, our workload can scale linearly. Okay? Sounds interesting? That was marketing. Let's talk about reality. Of course, reality currently looks a little bit different. Let's have now a more detailed look on In Memory OLTP. So the first step, I will cover memory optimized tables, then we move on to native compiled stored procedures, and finally I will also talk about those new lock and latch free data structures. When we create a table in SQL Server with the traditional create table statement, then we can tell in our SQL Server that we want to create that table as memory optimized table. Means SQL Server holds the complete table in main memory. Means every time when you're restarting SQL Server reads the complete table in main memory. When you afterwards read from that table, everything is just done in main memory. Means there is no need for reading to access your storage anymore. Of course, when you change data, we still have to write the data to durable storage if we want that, because otherwise we would lose our data. When we create a memory optimized table, we can also define up to 8 different hash or range indexes. That's already the first limitation. When you deal with a memory optimized table, you can only have up to 8 indexes. When you think back, the traditional old SQL Server supported up to 999 non-clustered indexes. Of course, when you hit that limitation, you have already failed and a huge amount of different other performance problems. But here, we have just the possibility to create up to 8 indexes, hash index or range index. A hash index is mainly used when you're searching for specific records in your table. So when you make singleton point lookups, when you want to perform seek operations, you're searching for a specific order, you're searching for a specific customer. So when you're expecting a very, very low cardinality in the result set, mainly one row, and a range index, as the name already implies, can be used when you're selecting a range of records from a memory optimized table. For example, you are interested in all your customers from London. You're interested in all your orders from the current month. Means when you create your table, you have to define which hash indexes and which range indexes you want to have on your table. And in addition, SQL Server also persists the data that we store in that memory optimized table in a so-called file stream file group. File stream is a functionality that was introduced back with SQL Server 2008, and In Memory OLTP uses that file stream file group to persist our data in a very, very fast, efficient way so that the data gets durable. Means when you're restarting SQL Server just reads that data from the file stream file group and just rebuilds your table in main memory. When you create your memory optimized table, we also have a so-called durability option. Means we can tell SQL Server if we want to persist our data. The default option is schema and data. Means you are persisting your table schema and you also persist the table data itself in the file stream file group. That's just the expected behavior. Means when we restart SQL Server, we still have the data in our table. We are not losing any records. As a side effect, because we are persisting that data across SQL Server restarts, SQL Server also has to log every transaction in the transaction log. So SQL Server also guarantees us the ACID properties of a transaction. So even if you work with In Memory OLTP, you have atomic transactions, you have a consistency, you have an isolation, as we will see later, and if you want, your transaction will be also durable. If you don't want to persist your data, you can also tell SQL Server that you want to create a memory optimized table which just persists the table schema itself, not the data. Means when you're restarting SQL Server, you have an empty table. Means when you're working with a schema-only table, there is no physical interaction with your storage anymore. You don't need to write the data into the file stream file group, and you don't need to log that transaction in transaction log. Because there is no roll forward, roll back, nothing. During the crash recovery, you just start with an empty table. As I've already said, schema only doesn't make sense for every possible table. Imagine you have a web application, users are entering their orders. In that case, you don't want to lose any record when your SQL Server crashes. So schema only makes sense in some specific scenarios, but not in every possible scenario. When we create a memory optimized table, amazing things are happening in SQL Server. You have your create table statement, and SQL Server takes that create table statement and converts your table definition to C code. That C code is afterwards compiled and linked into the DLL file, and the DLL file itself is loaded into the process space of SQL Server.exe. Means your table itself is just a native data structure. We have just enhanced the native code base of SQL Server.exe when we create a memory optimized table. Just think about that. As you will see later, there are also some implications with that approach. When we talk about other features in SQL Server, for example, querying that tables just works. Means you can make a select from that memory optimized table, you can make an insert, update, delete, just works. When you make a backup of your database, your memory optimized table is still part of that backup. When you think about high availability technologies like always on database mirroring, it just works with memory optimized tables. So let's have a look on that in the first step. I start here completely from scratch with a completely new database. So, the first step, I just create a new database, and as I've already said previously, In Memory OLTP relies on a file stream file group. So in the first step, we have to add to our database a file group which contains memory optimized data. That file group that we are adding here is mainly a file stream file group that you already know from SQL Server 2008. Then we use our database, and finally we just add into that file stream file group a storage container. So we just point to a folder in the file system where SQL Server stores that data. Again, that's just traditional file stream, nothing special here. Means we can also go to the file system, look into that folder. As you can see, that's just a traditional file stream folder, so nothing special here. Within that folder structure, SQL Server will afterwards persist our table data when we create a memory optimized table, and we specify that we also want to persist the table data itself. So in the next step, I create here a traditional memory optimized table. So I have a simple create table statement, and I say memory optimized equals on. This is the indication to SQL Server that we want to store the data of that table directly in memory, and I specify the durability option. Here you have the option for schema and data, which is also the default option, so you don't need to specify it, or schema only. When you create a table with schema only, you lose your data when your SQL Server crashes, when you restart your SQL Server. And you also need a primary key constraint. And in that case, I'm enforcing my primary key constraint with a non-clustered hash index. Means in the background, SQL Server creates a hash table, and for that hash table, SQL Server has to know how many so-called hash buckets we create. Internally, a hash table has multiple hash buckets, and here during the table creation we have to specify how many hash buckets we want to have. The idea behind that hash bucket count is that you have in every bucket just one record, so that you have no hash collisions. As you will see later, hash collisions are very, very expensive regarding CPU time. So here during your table creation statement, you already have to know how many records you are expecting in that table over the time. Just think about that. When we create now that table, you will see that the create table statement takes a little bit longer as usual. As you can see, took around 500 milliseconds. So from that perspective, very, very slow. But magic things have happened in SQL Server in the meantime, in those 500 milliseconds. SQL Server has taken that table definition, converted the table definition to C code. The C code was compiled to an object file. The object file was linked to a DLL file, and the DLL file was loaded into the process space of SQL Server. Means when you're now working with that table, you're just working with a native compiled data structure, as you would program it. You can also see in system OS loaded modules that we have now a so-called XDB native DLL. That's the DLL which represents our table. XDB stands for Extreme Transaction Processing. So we want to have an extreme performance improvement. We can also look at that DLL in the file system. I have here subfolders. That's the database ID. In our case, we have a database ID of 9. And here you have a C file, for example. And the C file is your table definition. We don't need to understand that. Just the C definition of our table. That C file was compiled to an object file. The object file was linked to a DLL file, and the DLL file was loaded into the process space of SQL Server.exe. So a lot of things and magic that happened when we created that table. Now we can insert a record. Just works. We can select rows from that table. We get back the 3 rows. In that case, when we look at the execution plan, SQL Server scans the complete hash index. Means SQL Server scans every hash bucket of that hash index and returns us back those rows. When you're searching for a specific record and you have on that specific column a hash index, SQL Server can make a hash index seek operation. So we're just seeking into a specific hash bucket. When we have no hash collisions in that hash bucket, we just return that specific record. Very, very fast. As you can see here, everything happens in main memory, so your elapsed time is mainly in milliseconds, 0 milliseconds, because everything happens within nano or microseconds. Just think about that. That's extreme transaction processing. You can update a record. Again, the first step, you're searching that record that you want to change, then you compute the new values, and then you make the update of the table. And finally, you can delete everything from that table, means your table itself is again empty. So insert, update, delete, select, just works. Nothing special here. When you create a table with the durability options, schema and data, you always have to specify a primary key constraint. When you haven't specified a primary key constraint, like here, the creation of the table will fail. So SQL Server tells us here, a table with the durability option, schema and data always must have a primary key. Primary key is always a good idea, because we want to uniquely identify our records in that table. On the other hand, when you create a table with schema only, so you tell SQL Server, hey, I don't care about my data, then you don't need a primary key constraint. Don't ask me why. Just a difference. Means in that case, when we are inserting, when we are changing, when we are deleting data in that table, everything happens in main memory. There is no physical interaction with our storage subsystem anymore. We don't write into the file stream file group. We don't log anything in the transaction log, because there's no crash recovery. There is no need to perform a roll forward or a roll back when we restart SQL Server. We just start with an empty, fresh table. Very, very fast, but of course you lose your data. Every memory optimized table needs at least one index, because the index itself is just a data structure which brings all the various rows in that table together. So the index itself links the rows together, means when you create a table without any index, that's not possible. In the traditional SQL Server world, it would be possible. It would be just a heap table, a table without a clustered index. With a memory optimized one, we need at least one index. A traditional clustered index is not possible. So you are not allowed to mix clustered indexes, non-clustered indexes with hash and range indexes. Those are just two different worlds in SQL Server. You can also enforce a primary key with a non-clustered range index. Means when you just specify here non-clustered, then you create a range index in the background. As I've already said, a range index is mainly used when you expect a very high cardinality from that table, so a lot amount of rows. So range index should be also always used when you expect a large amount of rows, a hash index when you just expect a few rows, mainly one row. That case, when you just say non-clustered, then you create a non-clustered range index. When you specify a hash, then you create a non-clustered hash index, and you also have to specify the bucket count that we have seen previously. So this also works. The largest limitation that you have, you can't change your table definition at a later point. Because as I've already said, SQL Server creates a DLL file. You can't change that DLL file during the runtime anymore. Means when you later decide you want to have an additional index on that table, it's not supported. When you want to drop an index that you are not using, it's not supported. When you want to change an index, for example, you want to change the bucket count of a hash index, it's not supported. When you want to change the bucket count, you have to drop and recreate your table. When you drop your table, you lose your data. Just think about that. Means the complete table definition with the complete index definition must be specified in one large create table statement. That's the first largest limitation that you have. You can't change your table definition later. Imagine you want to add a new column. Not supported. Check constraints. Not supported. Foreign keys. Not supported. Think about referential integrity. No way to enforce a referential integrity currently within In Memory OLTP. The only support that you have is a primary key constraint, a foreign key constraint, check constraints are not supported. Just think about that. Means when you have an existing database, migrating that database, some specific tables, can be a real challenge because you're losing your referential integrity. Think you have a badly written application which violates that referential integrity. Identity columns are also supported for a primary key constraint, which wasn't supported in the previous CTP version. So now in the RTM version this just works. When you use an identity, you always have to use a seed and increment value of 1. When you use other values than 1, it's not supported. Meaning in that case, with a seed and increment of 2, the creation of the memory optimized table again just fails. You can use all the, let's say, traditional data types in SQL Server, everything except LOP data types. So as you can see, I have played here with the various data types. They are all working. One of the limitations that you have is that the row size of a record can't exceed 8060 bytes, even when you have variable length columns. So when you want to migrate some existing tables to memory optimized tables and the existing table exceeds that row size of 8060 bytes, it's not supported. Just think about that. You have only the possibility up to 8 indexes. So in that case, I want to create 9 indexes, 9 non-clustered range indexes, not supported. Currently, we only have up to 8 indexes per table. It's just a hard-coded limitation internally in SQL Server. When you create an index on a character column, char, varchar, nvarchar, and so on, it doesn't work by default. So when you create that, it's not supported because the character columns must use the bin2 collation. Means you have to change your collation. When you change your collation, you are changing your sorting order, and you're also changing the way how SQL Server makes a comparison. Means your existing queries can return you a different result. So in that case, you have to use a collate, whoever runs the bin2 collation, and then you can create your index, your hash or range index on that character column. But you're changing the way how SQL Server deals internally with that data. You're changing the sorting order, you are changing how SQL Server makes internally the comparison. Questions on that? Yeah?
Is the timestamp a row version type supported in memory tables?
No, a row versioning itself is not supported because In Memory OLTP internally uses a row versioning.
Okay.
Everything in Memory OLTP is based on MVCC, multi-version concurrency control system. Means you have just optimistic concurrency out of box. Therefore, there's also no locking, blocking, and latching anymore. When you start a transaction in Memory OLTP, you just assume that that transaction will succeed. You're just thinking optimistic. Of course, that optimistic approach doesn't always work. Means when you commit your transaction, the transaction goes into a so-called validation phase, and during the validation phase, SQL Server just validates if your transaction is still consistent regarding the chosen isolation level. And in the validation phase, your transaction can fail. Okay? So just a completely different way. There is no pessimistic concurrency anymore. You just run every transaction optimistic. And during the commit time, the transaction enters a validation phase, and in the validation phase, the consistency of the chosen isolation level is just validated.
So do you mean the row version is implicitly available on the row?
Yes,
yeah.
yeah.
It's just there.
You are dealing with multiple versions. Means when you make an update to a record, you generate a new row version. When you make a delete, you generate a new row version. Of course, in the background there's a garbage collector, and the garbage collector just runs periodically and just purges out older versions which are not needed anymore. Means within Memory OLTP you need a huge amount of RAM, because you also have to think about the row versions. Microsoft recommends to have the double amount of RAM as you have data in that table. So for example, when you have a memory optimized table with 50 gigabytes of data, Microsoft recommends to have at least 100 gigabytes of RAM only for that specific table. To store the various row versions that you are generating when you are working with that table.
So sorry, is TempDB not used then at all?
No. Nothing happens in DempDB. Means the whole row versioning is just in memory. Everything is in memory. So you are not touching here in any way DempDB as you would do it with optimistic concurrency that was introduced back with SQL Server 2005 with read committed snapshot isolation and snapshot isolation. Everything just happens in memory. Yeah?
In your demo, you specified the bucket size to be 1024.
Yeah.
What does that number signify? Is it number of records you can have, or is it a...
Let's have a look on that. Let's have a look on that, how the bucket count influences the performance. I show you here another demo. So I've just prepared a new database and I create a simple table with a bucket count of 1024. So SQL Server always rounds up to the next power of 2. Means when you create a bucket count of 1000 you get 1024. Means in that case when we create that table we get internally a hash table as a data structure, and within that hash table we have 1000 hash buckets. And the goal of a hash table is always that you have no hash collisions. Means in every hash table in every hash bucket you just should have one entry. In our case the entry is a record. If you have multiple entries in one hash bucket, it leads to a hash collision. Means you have just a linked list in that hash bucket that you have to follow to retrieve records or to insert a new record into that hash bucket. I create here native compiled stored procedure. I talk about native compilation later. For us, it currently means we are running as fast as possible. No interaction with our storage subsystem. And I'm just inserting in a while loop 1 million of records. Means with 1000 hash buckets, we have on average in every hash bucket 1000 records. So a huge amount of hash collisions. I'm running that stored procedure, native compiled, very, very fast is very, very slow. Think about it, we are inserting 1 million of records and we're doing everything in main memory. Takes a 1 minute. Because we have a huge amount of hash collisions. Just think about that. You have to know the cardinality of your table, how many records you are expecting in that table when you create your table.
So, what is the general rule? If you've got, let's say, 1 million records, is a bigger pot better, smaller pot? What is sort of the general pattern of better performance?
Well, when you have an expectation of 1 million of records, you need at least 1 million of hash buckets. And every hash bucket itself costs you 8 bytes, because it's just a 64-bit pointer. Means you also can't create an unlimited size of hash buckets because you would waste a huge amount of main memory.
So you have the compromise when you set it up of an expected figure where you hope to get ultimately 1 record per hash bucket.
Yeah.
In the real world, you're probably going to have 4, 8, maybe if it because of the rule you cannot alter an in-memory object.
Yeah.
Now, quick follow-up, a slightly different topic on this. I'm assuming in memory optimized stored procedures you can only access memory tables.
Yes.
You can basically file storage tables, file storage stored procedures, and memory tables and memory stored procedures live in different worlds.
Yes.
Those
are just 2 different worlds.
Yes.
That's one of the limitations that we will see later when we talk in more detail about native compiled stored procedures. You are right, you can only access a memory optimized table. Means that's just a one-way direction.
So, what we have here is we have the memory version and we have the disk version, which is being synced up. Now, can is that disk version available for use or not?
No, you can't access
So it's
it.
an invisible. It's an invisible.
It's not possible to create such a stored procedure, as we will see later.
No, but you say it creates a physical database. It writes records physically.
Yeah.
Syncs them down.
Yeah.
But that is almost an invisible. Is that effectively invisible to the?
Well, you can query it in a traditional interpreted execution plan when you have a traditional SQL statement or a traditional interpreted stored procedure.
And is the asynchronous? Is it both dual way or single way? When you write to the memory, it syncs, it asynchronously updates.
Yeah.
What happens if you did the file system, or if you put a record in the file system version? Is that not possible?
That's not possible, no.
So it's just a physical permanent storage record of the in-memory version?
Yeah.
Right, okay.
Yeah. So as you can see here, the whole stored procedure inserting 1 million of rows took around 50 seconds because we had generated a huge amount of hash collisions. We have also a dynamic management view called system.db xdb hash index stats, and that dynamic management view tells you for every hash index how many hash buckets you have and how many records you have in every hash bucket. And as you can see, we have here almost 1,000 records in every hash bucket. So a huge amount of hash collisions. Means we want now to change the hash bucket count. Means in that case, we have to drop our stored procedure because the stored procedure is always generated as schema binding, and you also have to drop your table because you can't change that table later. Means in that case, when we drop that table, we are losing our data. Just think about that, just to change the hash bucket count. So I take here now a hash bucket count of 1 million. I recreate that table. I recreate the native compiled stored procedure. And now I run that stored procedure. Finished. Just think about that. That's the difference based on the hash buckets that you generate and provide to that hash table, to that hash index. Just think about that. 50 seconds versus 750 milliseconds. So you have to estimate how many rows you are expecting on that table. When you're over that estimation, In Memory OLTP will not be very fast anymore. Just think about that. So I've done here some tests, and you can see how the performance improves when you're going up with your hash bucket counts. Of course, when you afterwards provide more hash buckets, like 2 million of hash buckets, your performance doesn't get better anymore. In that case, you're just wasting a huge amount of memory, because every hash bucket needs 8 bytes. In that case, you are wasting 8 megabytes. Just think about that. So the sizing of that hash bucket count is very, very important. But you have to know how many records you are expecting in that table.
Question.
Yeah.
What if you have a table where you perform a lot of insert as well as delete?
Yeah.
So number of records kind of stays the same, but you're constantly removing record and adding new record.
Yeah.
Is that okay?
That is okay, yeah.
Okay.
That's no problem. So that's the story about memory optimized tables. Very, very fast with a lot of different restrictions, as we have seen. Let's continue now with native compiled stored procedures. In the traditional SQL Server world, when we execute SQL statements, when we execute stored procedures, the query optimizer compiles us the physical execution plan, and finally that execution plan is executed during runtime. And the execution of that execution plan is interpreted. Means interpretation is very, very slow and costs you a huge amount of clock cycles. As we have said in the beginning, currently when we look on CPU cores, we are limited with around 2 to 3 gigahertz of clock speed. Means we have a finite set of CPU cycles, and those finite set must be used as efficiently as possible. Means every time when we run a traditional execution plan in SQL Server, we are wasting a huge amount of clock cycles based on that interpretation. So that's one of the largest problems. What we can do now, when we create a stored procedure, we can tell SQL Server that we want to compile that stored procedure to native machine code. Means, again, magic happens in SQL Server. SQL Server takes the implementation of that stored procedure, converts the implementation to C code. The C code is again compiled into an object file. The object file is linked into a DLL file, and the DLL file is again loaded into the process space of SQL Server.exe. Means, when you afterwards run that stored procedure, you just execute machine code, which is amazingly fast with some side effects. As we have already said.
Can I just ask a quick question on that? So
Yeah.
you said natively compiled stored procedures can only query in memory tables, but
Yeah.
if you have a non-natively compiled one,
Then you can
query both?
Then you can query both.
Right.
Means when you have created a native compiled stored procedure, you are only able to access your memory optimized tables. When you have a traditional interpreted stored procedure, you can access disk-based tables, the traditional ones, and also memory optimized ones.
So, if you had, for example, reporting system, you'd have a traditional stored procedure to populate the in-memory table, and a native compile to go and do the actual
For example,
reporting services to grab that data warehouse data.
Yeah, that's possible.
What about functions? Can you have natively compiled functions?
There are some restrictions which functions you can use. So when you look into books online, you see a whole chapter which just deals with restrictions. So you can't use every possible DSQL function because the DSQL function itself must be converted to C code.
Right.
The
So
implementation of the
own
function.
Own SQL functions like inline or multi-statement functions?
No.
Right.
For example, parallel execution plans are not supported. Your stored procedure is just executed serially. Let's have a look on those things. Again, I just create a new database. And I create a simple memory optimized table, primary key enforced as a non-clustered hash index, and I choose here a bucket count of 2 millions. Means just the creation of that table takes around 16 megabytes of memory. I also specify here the durability option schema only. Means when we are working now with that table, we just work in main memory. There is no physical interaction with our storage subsystem. Nothing gets written into the file stream file group, nothing gets logged in the transaction log.
So if you back up a schema only table, does it actually get backed up to the schema and the data?
Only the schema. You don't need to back up the data.
So
doesn't make sense.
Store it, do you need some kind of initiation startup process to rebuild that data in?
Yeah. So a schema only table is only recommended for some transient data. Think about temp tables, staging tables when you are populating your data warehousing scenario. And now I create a traditional SQL stored procedure. So just a traditional stored procedure, and again I'm just inserting in a while loop 1 million of rows. We have 2 million of hash buckets, no hash collisions, nothing. I just want to show you how slow and interpreted SQL stored procedure is. We have no hash collisions, we are not logging anything into the transaction log, we just make everything as fast as possible in main memory with an interpreted traditional stored procedure. When we execute that stored procedure, it takes a very, very long time. Almost 2.5 minutes. Just think about that. I'm canceling that. Don't want to waste that time. But you can see we have written records into that table. We have here around 200,000. So take some time. Let's drop that interpreted stored procedure. And I drop the table. I want to get rid of the data. A truncate, for example, is not supported. Truncate table, not supported. In that case, you can delete the data, I drop it, and just recreate the same table again. And now I create a native compiled stored procedure. So you can say now, with native compilation, means when we create that stored procedure, the implementation of that stored procedure is converted to C code. C code is again compiled and linked into the DLL file, and the DLL file is loaded into the process space of SQL Server.exe. A native compiled stored procedure must be always generated as schema binding, means you can't change the underlying tables anymore. Of course, here with a memory optimized table, it's even not possible. But you can't drop the table because the table has a dependency to the stored procedure. You also have to specify the security context during the creation, because the security context must be checked in the generated C code. Just think about that. You can't make that decision during runtime. And then you have a so-called atomic block, and within the atomic block, you have to specify your transaction isolation level, because the transaction isolation level must be also chosen during the compilation, because it must be enforced in the generated C code. Means you can't change on the fly during the execution of that stored procedure your isolation level, and you also have to specify your language. Error messages. SQL Server has to know during compilation in which language error messages are returned. And the isolation level snapshot that we are using here is just read committed. Gives you the behavior of read committed. Means you have no dirty reads and you also have no repeatable reads. Just the default behavior of read committed. And then again, in a while loop, we just insert 1 million of rows. I create here, to prove that, another table which is just a disk-based one. And when you try to reference that table in your native compiled stored procedure, then the creation of that native compiled stored procedure doesn't work, because you are referencing a table which is not a memory optimized table. So as soon as you're natively compiling your stored procedure, You have only access to memory optimized tables. That's also very, very important. So let's create that now. As you can see, takes again a little bit longer as usual because again magic happened. When we go back to the file system, when we refresh it, you can see we have now more files. First file here is now the implementation of our stored procedure as C code. That's your stored procedure. That C code again was compiled to an object file. The object file was linked to a DLL file. The DLL file was loaded into the process space of SQL Server.exe. And as you can see from the C code, they are using spaghetti code. Go do. When we write such a code, we have some problems. That's on purpose. There are no functions in that generated C code because a function call is more expensive as a go-to statement, because the go-to is just on the assembly level a jump instruction. With a function call you have to prepare your whole stack frames. So as you can see, that's really extreme transaction processing. We want to execute that stored procedure with the least amount of CPU instructions. Therefore, we have spaghetti code with go-to statements. Just think about that. Let's execute the stored procedure. Finished. We've inserted 1 million of records. That's the difference between an interpreted stored procedure and a native compiled one. The interpreted one would take around 2.5 minutes to insert 1 million of records. The native compiled one completes with the same amount of work in just 600 to 700 milliseconds. Just think about that. That's a huge difference. You're just executing native compiled machine code. Nothing more, as fast as possible. I delete again the data from that table. And I want to show you something else with native compiled stored procedures. I'm including the actual execution plan, which tells us during runtime what happened during the execution of that stored procedure. Here is your execution plan. You have no execution plan because this is your execution plan. You're just executing native compiled code during runtime, means SQL Server can't give you an actual execution plan. There is no execution plan, no actual execution plan. The only thing that you have is the estimated plan. Because when SQL Server compiles that stored procedure down to native machine code, the stored procedure goes to the query optimizer. The query optimizer compiles us the estimated execution plan, and finally, the estimated execution plan is compiled down to C code. But as you know, the estimated execution plan is just an estimation. Means from a performance tuning perspective, you have almost no idea what happened during runtime. Imagine you see your native compiled stored procedure takes 2 seconds instead of 600 milliseconds. You can't ask SQL Server for the actual plan anymore. There is no actual plan. That's your plan. C code. Have fun. Just think about that. Because it's natively compiled, you have no recompilations. Imagine your statistics are changing. Maybe currently you are seeking into a hash index because you're just expecting one row. Afterwards, you are changing your data distribution, you are inserting a huge amount of additional rows, and instead of 1 row, you are getting back 10 millions of rows. You're still stuck with the old execution plan. So there are no recompilations that SQL Server recompiles you that execution plan to get a scan of that hash index. Means when you want a new execution plan for your natively compiled stored procedure, you have to drop and recreate it. Cool. When you drop your stored procedure, you're losing all the security permissions that you have granted. So from a performance tuning, performance troubleshooting perspective, amazingly, as a consultant. Yeah, question.
So might it help if you've got quite a complex query that was pulling from several memory optimized tables and doing joins? Might it help to actually pre-populate them with some data so that when it creates that C code, it has some idea of the sources to expect? When you expect 100 more of those and those.
When you create your natively compiled stored procedure, you should have a realistic data in your table. So that you get a good enough estimated execution plan. But of course, that data can change over time. And then you're still stuck with the old generated estimated execution plan. So in that case, the only option that you have to drop that stored procedure and just recreate it to get a new, better performing execution plan, which is again optimized on your current data distribution.
So could that be part of your maintenance, database maintenance plan, that every now and then you do drop, recreate and reapply permissions as part of a maintenance plan?
Yeah, for example.
So what does that mean? What about changing the code by an alter procedure? Is that possible?
Sorry?
Changing your code using an alter procedure?
To upgrade. There's no alter.
So there is a gap then when you have no procedure?
Yeah. So when you want to change your implementation, you have to drop and you have to recreate it, because you need a new DLL file, a new native compiled implementation. So as you can see, there are already some serious side effects. But it's very, very fast, with some drawbacks.
Are these all drawbacks that you think might be fixed or improved in future versions?
I hope so. Otherwise, nobody will use it. Come on, who on earth will use that currently? Nobody. Doesn't really make sense.
There's nothing that can't be fixed due to the way the technology works.
Let's see what Microsoft brings us in the future. But currently, I'm not really recommending it because it doesn't make sense. A lot of people are coming to me and telling me, hey, we want to use In Memory OLTP. After 5 minutes, no. That's a very, very easy talk.
So do you have any visibility on what's changing in 2016?
No idea on that. I'm not living in the future anymore. Because everything that you know from the future will change. That's always the problem. But of course, it's just a version 1. It's an amazingly technology, and Microsoft has to change things. Microsoft has to remove those limitations, and when those limitations are removed, it's an amazingly fast technology.
Yeah, is there an event you can hook into when the server restarts? Because you said sometimes you might need to preload if you're not using schema. If you're not using schema and data, for instance. Is there something you can hook into when the server restarts to populate an in-memory table?
Well, every time when you restart SQL Server, SQL Server takes the definition of your memory optimized tables and your native compiled stored procedures and recompiles them. Means the DLL files that we see in here in the file system, that's just debugging for Microsoft and for us having fun. Means you can drop them because everything is just already loaded in main memory. And when you restart SQL Server just takes the metadata of your table definition and compiles you a new DLL file.
I assume that it copies the data, resyncs the data back
Of course, yeah. Which also has some implication because the restart of your SQL Server takes longer because you are compiling DLL files. As you have seen, a simple table definition, a simple stored procedure takes you half a second. Means when you perform failovers, cluster failovers, the cluster failover will take longer.
How does it perform with, I've got a search engine system, relies a lot on full text searches.
Yeah.
What is its performance when it's doing the equivalent of in contains or industry? What kind of performance are you going to get on that? Because currently we're heavily dependent on full text indexes.
I have no idea on full text indexes. Never ever worked with them.
What's the performance? Do you know what performance is like when you're doing full text? When you're doing text searches?
Yeah.
And
I can't answer that question. I have no idea on full text.
okay.
Yeah.
Presumably it's not supported, right?
Sorry?
Presumably it's not supported. You can't have a full text index on the in-memory table.
No, I don't think so. I don't think so. So as you can see here, we have a huge amount of limitations. I just want to show you a few more things about optimistic concurrency. As I've already said, when we are working with In Memory OLTP, every transaction just assumes optimistically that the transaction will succeed. When we finally commit our transaction, the transaction goes into a validation phase, and in that validation phase, SQL Server again validates the semantics of the chosen isolation level. I create here a simple memory optimized table, and I just insert a few records. The first thing that you will encounter when you are working with explicit transactions and just with interpreted T-SQL code is that the transaction will not work anymore, because for those transactions you have to specify the isolation level as a query hint. So for example, we can say here with snapshot, and as I've already said earlier, snapshot is the traditional read committed isolation level in memory OLTP. Means when we specify here with a query hint the isolation level, our transaction succeeds. There's also a database option called memory optimized elevate to snapshot. Means when you set that option to on, then you don't need that query hint. Means every transaction which accesses a memory optimized table runs in the snapshot isolation level. That's the first thing that you will encounter when you're working with transactions. Let's demonstrate now some conflicts, some optimistic conflicts that can occur when you run with multiple concurrent transactions. I have here a simple transaction which updates the first record. I run that transaction in a second session, and as you can already see, the transaction is aborted. Normally, in the traditional pessimistic SQL Server world, that transaction will be blocked because the first one has already acquired an exclusive lock on that record, means the second transaction will just wait. Here we have a so-called writer-writer conflict because two transactions have tried to change the same record at the same point in time. Means for your application, In Memory OLTP is not really transparent. You have a new error message number, you have to react on that error message number. Just think about that. Because we are optimistically assuming that every transaction will succeed.
Is that different from recommitted snapshot or snapshot on normal tables, isn't it?
In every other transaction isolation level, that second transaction will block. Because with read committed snapshot isolation or snapshot isolation, you just influence readers' select statements. But your update statement will be still blocked because a writer still blocks a writer. But here, with optimistic concurrency, with that multi-version concurrency control system, things are changing. There are no locks, there are no blocking anymore. Therefore, we have here a simple writer-writer conflict.
There's no exclusive locks at all?
Nothing. When we run that, and when we go to system logs, where request session ID equals 52, you have just a database log, the shared one, because you're using that database, and you have a schema stability log on the table itself. In the traditional SQL Server world, you would have an exclusive log on that record, an indent exclusive log on the page, and an indent exclusive log on the table level. There's no locking anymore. We're just running optimistically our transactions. I have here another conflict, the so-called read-write conflict. I begin here a transaction and I tell SQL Server I want to have repeatable reads. Means we want to have a so-called read stability. Means when we are reading those records multiple times in our transaction, we want to see the same records. Default isolation level repeatable read. In the default SQL Server world, when we are running in the isolation level repeatable read, SQL Server acquires our shared logs for reading, and those shared logs are released at the end of our transaction. Here things are changing. I'm running here the first transaction. I have here now repeatable reads, and I have here now a second transaction which just updates those records that we have already read here. In traditional SQL Server world, that update will be blocked because the other session has a shared log and the exclusive log is blocked by the shared log. As you can see, the update works and you still have in that transaction repeatable reads. But now, when you commit your transaction, that transaction goes into a validation phase, and during the validation phase, SQL Server just checks if these records have changed. If these records have changed, we have violated the semantics of the isolation level repeatable read because we have no read stability anymore, and your transaction will fail during the commit. Just think about that. Optimistic concurrency. We assume that the transaction will succeed until we commit that transaction. Just think about that. Isolation level serializable. You want to prevent phantom records, completely new records, when you are reading a set of records. I begin a new transaction. I say I want to have the isolation level serializable, means I want to have a read stability and phantom avoidance. And I have a second transaction, which just inserts in that set that we have read here one additional record. Means we are violating the semantics of the isolation level serializable. We still have here rebuildable reads. We can't see that new record, so we have the phantom avoidance. But when we commit that transaction, it will fail because we have a validation failure because of the isolation level serializable. Okay? You can also have errors in the isolation level snapshot, which is read committed. Just think about that. I create a simple new table, and I have two transactions which are inserting the same primary key value of 1. Wow. Let's commit the first one. Let's commit the second one. Ouch. Again, optimistic concurrency. There are no locks, therefore there is no blocking anymore. The semantics of your transaction are just violated when you are committing that transaction, when the transaction goes into that validation phase. It's a completely new way how you are working in SQL Server with In Memory OLTP, with some side effects.
Are you going to give us any tips on how to deal with that, or do you not know yet?
Don't use it now. Very simple. Because you also need the right problems. And the question is, who has right problems? Who needs that amazingly fast performance? I would say normally, when I'm dealing with SQL servers which are bad performing, around 90 to 95% of all problems can be solved with indexing. Work on your indexing strategy and your SQL Server will be amazingly fast. Of course, when you have a bad indexing strategy, your SQL Server will be slow. Of course, there are some really, really rare scenarios where In Memory OLTP can make sense, but really, really rare scenarios. So the question really is, who needs currently this technology and who wants to use that technology with all the various limitations that we have? We can't change a table. We have no recompilations in the native compiled execution plan. To be serious, you can't use that with those side effects. I'm skipping here lock and latch free data structures because I have tomorrow also a session about unique identifier values as primary key values, and I will also talk about these things tomorrow, and I will also show here the same stuff, the same samples. Therefore, I have shown you today the things about the isolation levels that we have seen, and you will see the same thing tomorrow in my session about the unique identifier values. Therefore, I'm just skipping that. Doesn't make sense to present the same thing 2 times to almost the same audience. Limitations. Yeah, it's integrated in SQL Server, but we have a large but. We've already seen a huge amount of different limitations. No constraints, no foreign key constraints. Forget about your referential integrity. Largest limitation, you can't change your table definition at a later point in time. If you need an additional index, if you want to drop an index, if you want to change the hash bucket count of your hash table, drop and recreate your table. Means you're losing your data, means you have to write that data in the meantime to somewhere else, to a different table. When this different table is not a memory optimized one, it will be very, very slow, because again, you're dealing with your slow storage subsystem. Just think about that. If you're writing your table to a different memory optimized table, you have to think about the size of your RAM. You need a huge amount of additional RAM to store that data in the meantime somewhere else. Stored procedures, we have only access to memory optimized tables. Okay, makes sense. The largest problem that we have is that we have no recompilations. Means you get one estimated execution plan and you are running that estimated execution plan forever. There are no recompilations. When your statistics are changing, nothing means when you want to have a new execution plan, you have again to drop and recreate your natively compiled stored procedure. So also some problems that we have here. Who of you like In Memory OLTP? As you can see, I'm a magician. I can change your mind in 90 minutes. Very simple.
I think the one use we can use it with, in spite of those limitations, is in our staging data. So
staging data, yeah.
We do pull large amounts of data from other systems, and then analyse and merge it with our live data. Yeah. And the biggest problem we've had with that, first of all, there's the time it takes to just put the data in the table. Yeah. But because all our customers tend to use full backups, it spams the transaction log immensely. So you're pulling down loads of data to merge a little bit of data, but the transaction log grows massively every time you do that. And deleting that data, again, it all ends up in the transaction.
Well, when you finally break it down, you mainly use it for temporary tables and for staging tables. And you use a feature which is called In Memory OLTP. And you use it for temporary table and staging tables. Doesn't really fit. This doesn't really fit. You can just use it for a very, very specific use case currently. But that's not the real main benefit where Microsoft is positioning that technology. The code name of In Memory OLTP was Hekaton. Hekaton is the Greek word for 100. Means we want to have a performance improvement of 100x. We are not talking about 100%. 100 times faster. When Microsoft first showed us that this technology, they have just switched a switch. And the needle goes from left to right. 100x improvement. Show me this with a production database, with foreign key constraints. Not possible.
So what about if you've got a schema and data table, so it's saving as well to disk.
Yeah.
When you do save, or when you insert some data, when is control returned? Is it like does the transaction log? It has to go into a transaction.
The
log?
first step, SQL Server writes into the transaction log, and then SQL Server also writes the data into the file stream file group. But writing to the file stream file group is again asynchronous in the background.
So it's
just
deferred. Synchronous and the file facing.
Yeah. But writing to the transaction log is still synchronous.
So it's just almost an automated insert or update or delete.
Yeah.
Because I'm thinking of this as for a search engine, having the front tables which are intermediate is in memory, and then because these get built each morning, so we'd be deleting it down, loading it up again, and having those as the very fast front-facing sort of search engine tables. So therefore, they don't change very often. Generally, they're basically destroyed and rebuilt in a specified maintenance window, and therefore we can search very quickly. We can search very quickly, and then it gets handed off to file-based tables to deal with the click-through.
As I've said, for some specific scenarios it can make sense, but currently not really for the broad range. A lot of people are just thinking, In Memory OLTP, great, let's enable it, and we have a huge performance improvement, but this is not really the truth.
So suppose I've got a schema-only one now, so it's purely in memory.
Schema only is purely in memory.
Right, now what have I got an always-on cluster, and I do a failover, have I lost it?
You start with an empty table. You are persisting the schema. You are telling SQL Server, I don't care about the data. Therefore, you don't interact with any storage anymore. You don't need anything in the file stream file group, because the table is not durable, and you don't need to log anything in the transaction log, because there's no crash recovery for that table.
So with schema only, it's also not logging the transaction log, is it? It doesn't need to be.
You don't need it. You don't need it.
Yeah, perfect staging.
If you want to know more about SQL Server and performance tuning, I'm coming back to London in the first week of June, and I'm running here my SQL Server performance tuning workshop, just 5 days about everything about performance tuning and troubleshooting in SQL Server. You can find more information about that workshop on my website, and if you give me a business card of you, I can also give you a 10% discount. So thanks for attending my session, and I'm already looking forward to see you tomorrow. Shared data structures, like data that we have put in main memory. SQL Server internally use a concept called latching. Means when you read a memory region within SQL Server has to lock that memory region in main memory so that nobody else at the same time can write that memory region. Means with latching you have blocking directly in main memory. Means as a conclusion, our relational database doesn't really scale very well. So those are the current challenges that we are dealing with when we are talking about relational databases. I have here a nice picture, and on that picture you see, for example, that blue line, and the blue line is just the CPU clock speed. And as you can see, over the last years, the CPU clock speeds are not increasing anymore. As I've already said previously, we are stuck at around 2 to 3 gigahertz of clock speed. More is currently not possible. Means we have a finite set of CPU cycles, and we have to use those CPU cycles as efficient as possible. As we will see later, in the case of SQL Server, when we run queries, SQL Server doesn't use those CPU cycles very efficient, because every execution plan in SQL Server is always interpreted, and interpretation means a huge amount of overhead regarding CPU cycles. Means when we now look on all those various programs, we mainly want to have a technology which stores all our data in main memory. Means we don't want to access our physical storage anymore. Of course, at some point in time, we still have to write our data to physical storage, because otherwise we would lose our data when our database crashes or when we're restarting our database. That's the first thing that we want to have. In the next step, we want to execute queries in our database with the least amount of clock cycles. As I've already said, we only have a CPU clock speed of 2 to 3 gigahertz. More is not possible. Means thank you. Means we want. Hello everybody. How are you? Ready for some fun? Perfect. So welcome to my session about In Memory OLTP, which is a completely new feature in SQL Server 2014. Who has already heard about In Memory OLTP? Who has already worked with it? What do you think about it? Good, bad?
I haven't tried it yet, but I'm looking to try and improve the performance of some of our updates and transactional-based updates, where we're maybe impacting tens of thousands of records in a small space of time. So that's what I'm getting.
Cool. Okay. So in this session, I want to give you an introduction to In Memory OLTP, why Microsoft introduced that technology in SQL Server 2014, We will see how we can work with In Memory OLTP, and because it's just a version 1 implementation, we also have to look on all the various limitations that we currently have with that amazingly new technology. Few words about my person. My name is Klaus Aschenbrenner. I provide with my company SQL version across Europe, SQL Server trainings and consulting services. I'm also a Microsoft Certified Master for SQL Server 2008, which was the highest technical certification that you could have achieved on SQL Server. I say was because that certification was just retired by Microsoft because they haven't made any profit out of it. So really strange story. I've also written the book Pro SQL Server 2008 Service Broker, which was published with April in the summer of 2008, so already a very long time ago. Service Broker is an asynchronous messaging framework that Microsoft first introduced back with SQL Server 2005, and with Service Broker you're able to write asynchronous message-based applications. Who of you is working with Service Broker? Just a few of you, so as you can see, I'm mainly working with things that nobody cares about. No, just kidding. You can also follow me on Twitter, and you find further information about my services about SQL Server on my webpage on sqlpassion.at, where you also find a lot of free training content around SQL Server. Let's have a look on the agenda for the next 90 minutes. In memory, very, very fast. We have also latency times of nanoseconds, and main memory compared to SSD storage is cheap. Very, very cheap. When you nowadays want to buy 32 gigabytes of RAM for a database server, it costs you just a few €100, a few £100, so not really too much compared to our expensive SSD storage. So that's the first problem. We can't store our data in a very, very cheap and very, very fast way. On the other hand, when we look on our CPU clock speeds, the CPU clock speed is not really scaling anymore. Who of you has a CPU with 10 gigahertz? Nobody. As you have seen over the last years, clock speeds were going up and up and up, and now we are somewhere at the plateau at around 2 to 3 gigahertz. More is not possible because of the introduced heating. What are doing the CPU vendors? They are providing us a lot of different cores within the physical CPU socket. So when you currently look on Intel processors, AMD processors, it's not really a big problem to buy one physical CPU socket which has, let's say, 20 individual cores. Of course, when we look on the software which runs on that CPU socket, it's very, very important that the software can use all those cores concurrently. The problem that we have with relational databases is the fact that the relational database doesn't really scale linearly. Means, let's say you have 100 users on your system, 100 users are giving you a throughput of, let's say, 1,000 transactions per second. When you increase the user load to 200 users, you will not have 2,000 transactions per second, because a database doesn't really scale very well because of the introduced locking and blocking. Means every time when we read records, when we write records, SQL Server has to lock those records. Means users are just blocking each other, users are just waiting on each other. Means our throughput doesn't increase linearly. And internally, when SQL Server want to execute our queries with the least amount of clock cycles, with a finite set of clock cycles, 2 to 3 gigahertz, and we want to make as much work as possible in that set of clock cycles. And in addition, we want to have a technology that avoids completely the whole locking, blocking, deadlocking, and latching inside our database. Means when there is no locking, there's no blocking, when we have no latching in main memory, our workload can just scale linearly. And guess what? That technology is in Memory OLTP in SQL Server 2014. In Memory OLTP itself is based on 3 different pillars. So-called in-memory optimized tables means when we create a table in SQL Server, we can tell SQL Server that we want to hold that table entirely in memory. Means when you're reading from that table, you're always reading only from main memory. You're not reading from your storage subsystem. When you write to your table, you also write only to main memory, and SQL Server just asynchronously writes out to your storage subsystem if you want to persist your data. You can even tell SQL Server, I don't care about my data anymore. Means in that case, when you're restarting SQL Server, you also have lost your data in your table. Not really recommended in every possible scenario, but for example, think about staging tables in an ETL process when you are populating your data warehouse. When that process crashes, you don't care about that because you just restart that process. Just think about it. Temporary tables, session state tables, they can be good candidates for memory optimized tables which you don't want to physically persist in your storage. In addition, we have a so-called native compilation. Means when you create a stored procedure, by default in SQL Server, the execution plan of such a stored procedure is always interpreted during runtime. And the interpretation just means we need a huge amount of additional CPU instructions, means the current amount of... The first step, I want to talk about the challenges why almost every database vendor provides us in-memory technologies. SQL Server provides us in-memory technologies, Oracle provides us in-memory technologies. The same happens, for example, for SAP. In the first step, I want to give you an overview why we now need in-memory technologies and what are the challenges behind it. The next step, we will look on the implementation of in-memory OLTP in SQL Server. So I want to show you what in-memory OLTP is and how you can work, and also how you can migrate your existing databases to that new technology. And in the end, I also want to talk about limitations. As I've already said, in-memory OLTP is just a version 1, means we have a huge amount of restrictions, and therefore currently you really have to decide if you really want to use that technology, because you are paying a lot for it based on the restrictions that you have in your database when you use that new technology. Let's talk in the first step about the challenges that we are currently facing. When we look on our storage subsystems are currently very slow. Who of you has a very fast performing storage subsystem? Almost, really? Wow, you lucky guy. But as you can see, almost nobody says today that we have very fast performing storage subsystems. Normally, when we deal with storage subsystems, we have slow rotational disk drives, means when we access those drives, a physical disk head moves forward, backwards, the platters are just rotating, means when we are reading to that storage, when we are writing to that storage, we have latency times of milliseconds. So very slow. On the other hand, We also have already SSD storage, SSD disks, very, very fast. We have latency times of nanoseconds and very, very expensive. Let's think about main memory.